Hello and welcome to this video on the series on water autoionization. My name is Eri Kim, and in this video we'll be describing the process of autoionization. We discussed in another video what an amphoteric species is. It's the ability of a molecule to donate a proton and act as an acid, or accept a proton and act as a base. The most common amphoteric species you'll encounter is water. This reaction really showcases this. We can pick this water molecule to act as the acid and donate its proton to form its conjugate base pair, the hydroxide ion. And we can pick this water molecule to act as a base and gain a proton to form the hydronium ion, which is its conjugate acid pair. Identifying conjugate acid-base pairs was also discussed in another video. The ability of water to react with itself is referred to as the autoionization of water, and forms a basis for an important concept in acid-base chemistry, the pH scale. KEQ is the equilibrium constant for any reaction, described generally by the concentration of the products over the reactants. Since solids and pure liquids like water do not figure into K equations, the KEQ for water is described by the concentration of the products alone. So the concentration of the hydroxide multiplied by the concentration of the hydronium ion, as described here. This is such an important relationship that we give it a special name, the Kw, which describes the equilibrium constant of water specifically, and has a value of 1 × 10⁻⁴ at 25 degrees Celsius. We can infer something interesting from the value of Kw. Since 10⁻⁴ is a tiny fraction of 1, the autoionization of water doesn't proceed in the forward reaction very much, and most of the water will stay as H2O. A neutral solution is one where the concentration of the hydronium and the hydroxide are equal. And using the Kw expression we discussed earlier, the concentration of both ions can be calculated by taking the square root of 1 × 10⁻⁴ to give us 1 × 10⁻⁷. The notation P is an equation, where P anything equals a negative log of anything. So pH is a negative log of the hydronium ion concentration, which is the negative log of 1 × 10⁻⁷ to give us 7. In the same manner, POH will also equal 7 in a neutral solution. All of this explains an important relationship in the pH scale. Taking our earlier equation where Kw equals the concentration of hydronium ion and the hydroxide ion, if we apply the negative log relationship, so negative log Kw equals the negative log of the hydronium and hydroxide ion concentration, and then we sub in that Kw value, we can use a log rule to separate out the hydronium ion and the hydroxide ion concentrations like so. Finally, the negative log of 10⁻⁴ is 14, and the negative log of the hydronium ion concentration is our pH, and the negative log of the hydroxide ion concentration is POH. This equation shows us a balance between the pH and the POH. For example, if I have a low value of pH, the POH must be compensatingly high to make the sum equal 14. We're going to use this relationship to solve some problems in our apply question. The first part of the apply question asks us to calculate the concentration of hydroxide given a hydronium ion concentration of 5 × 10⁻⁹. First, remember the relationship that links hydronium ion and the hydroxide ion, the Kw expression. Then rearrange to solve for the hydroxide ion, and then we can plug in our values, which is 1 × 10⁻⁴ for Kw and 5 × 10⁻⁹ for the hydronium ion concentration. This gives a hydroxide ion concentration of 2 × 10⁻⁶ moles per liter. In part B, we're given a pH value, and while we still need that Kw expression, we have to first convert the pH to a concentration of hydronium ion. Remember that pH is the negative log of the hydronium ion concentration, and rearranging that equation gives us this relationship. The concentration of hydronium is equal to 10 to the negative pH, since log is a base 10. Plugging in our pH value gives us a hydronium ion concentration of 10 to the -4. We can now use the rearranged Kw expression to solve for the hydroxide ion concentration by plugging in the values. So Kw is 1 × 10⁻⁴, hydronium ion concentration is 1 × 10⁻⁴, giving us a hydroxide ion concentration of 1 × 10⁻⁻⁰ molars. Alternatively, you can use the equation pH plus pOH equals 14 to calculate the pOH value to be 10. Then use a pOH equals negative log of the hydroxide ion and rearrange to this equation. Hydroxide ion concentration equals 10 to the negative pOH to give you a value of 10 to the minus 10 molars. Either method will give you the same answer. We reviewed a lot of equations and relationships in this video, so make sure you follow up with some practice questions. You want to be comfortable with understanding how pH is derived from the equilibrium constant for water, Kw, and how pH and pOH are related. This will lay the foundation for future problems involving acid-base strength, titrations, and buffers.